Well, I guess we can start. Welcome back, everyone. So we are done with chapter 5. It was kind of a short tour of eigenvalues and eigenvectors. We've made a quick look at chapter 6, looking into inner product orthogonality and other geometric ideas for vector spaces. And it's going to be a kind of a short tour as well because we're almost out of class time. So as far as week 15 goes, Tuesday is going to be an ordinary week. We're going to just finish up the last topics we're working on. And then Thursday, a week away from today, we'll be reviewing for the final exam. So we're nearly there. Congratulations, folks. Section 6.3 is going to be the last section of the semester, but assignment 6.1 is going to be the last assignment of the semester, mainly because I feel like I'm probably going to finish section 6.2 when we come back on Tuesday. 6.3 is also really short, but those sections being due or completed on Tuesday of next week doesn't give us the normal turnaround time for handing in assignments. And collecting assignments during finals week is usually kind of a sketchy thing to ask for. So this one is going to be our last assignment due December 11th. And for section 6.2, 6.3, the one we'll end on, I'll have suggested exercises just for additional practice. And because I don't have a full-on homework assignment set for these last two sections, 6.2, 6.3, I'm going to be highly specific on what problems you can expect to see on the final exam relative to those last two sections, so that there'll be a little less anxiety of what I'm going to ask in these last ones, so that'll help out with the studying. But that's our plan so far, folks. Any questions at all to start us out today? Okay, probably what will happen is when you come back on next week, though probably more like on Monday, I'll start sending out the instructions for scheduling your final exam. I'm going to have it completely written, completely proofread, and I'll send out that information on Monday for scheduling. But for the folks who have class in person, it'll just be like another exam, except it's 2 hours on Friday in this room from, let's double check that, 10 a.m. to noon, 12 p.m. For those people who are on the online section, it can be taken on Friday, the official date. It can also be taken any day of the week if you prefer to take it earlier. It's going to be pretty much up to your option. And it can be taken at any time of the day. Well, any last questions at all, folks, before we get started? Okay, well, let's return back to section 6.1, looking into the inner product. We did a really fast inner product or dot product between these two vectors. According to the definition, all we're doing is taking vectors. They come from the same vector space, Rn, in the definition, multiply the corresponding entries and add them up to get a scalar value. So our dot product is an interesting product of vectors resulting in just a scalar. And here we just did a couple of fast dot products. This one was 6 times, or excuse me, plus negative 12 for negative 6 altogether. And this was just saying rescale the vector v by that new scalar u dot v. So that's our kind of warm up, kind of fast one. These notes are kind of fun in a certain sense. There's nothing too heavy going on in these notes, kind of a get everyone on the same page kind of set of notes. But we'll do a couple interesting problems toward the very end of the document. So after the inner product's defined, it's kind of interesting that this weird numerical game is going to give us essentially all we need to know about the geometry of vector spaces to do interesting things like, say, calculus on Rn if we needed to. So going beyond that number game, here's some properties of the dot product. Critically, this theorem is false if you're working in a different kind of vector space. If you're working in Cn, the space of complex numbers with n entries, then some of these things are actually completely false. So keep in mind, this is only a valid theorem if you're using specifically real numbers. Part A wouldn't be true. In fact, the way we define the dot product isn't even accurate in the first place either. So dot products are specific to the kind of vector space you're working with. We have some nice properties. This is just a commutativity type property. U dot v is just v dot u. We have a type of distributive property. We'll be using some of these towards the last problems. If we have vector addition, dot product w, we can either do the vector addition first, or we can do the dot products first and then the vector addition in the middle. Likewise, we can reassociate, so the scalar multiplication can be done either first or last, or do it on the vector v, so this scalar can commute all the way through. And there's a nice result of positivity. This is going to be helpful for us when we go to define length, or the norm of a vector. For any vector in Rn, u dot u is non-negative. It's greater than or equal to 0, and you'll only get 0 if it was the 0 vector on the very big onset. So these are our nice algebraic properties with dot products. Last one, positivity, gives us now a little bit more geometry. Well, our first bit of geometry of vector spaces. If you grab a random vector like this v from Rn, then we'll say the norm of that vector, or more geometrically, the length of that vector, if you prefer to say, is this kind of double absolute value. So if you see those double bars, we're thinking the norm or the length. It's square root of v dot v. That's appropriate because this is non-negative. And when you take v dot v, you're just squaring the corresponding entries across v. The way this ties in with length is this is essentially just Pythagorean's theorem. If you took, say, a random vector v in R2, since it's easier to visualize, say here's our vector v. We'll have components v1, v2. Here's a line that goes through that vector v, the span of it. The length is just going to be the length of this line segment from here to here. And so using Pythagorean's theorem, because that's the origin, you would just take v1 squared plus v2 squared and take the square root. So we're just saying by the length, really just the distance between the origin and that vector v. If the length is 1, it's a special vector, which we'll call a unit vector, which has lots of interesting roles in calculus. And there's a nice little theorem here that we'll come back to when we practice this problem. So again, this is another not too heavy of a topic, possibly a refresher problem for you if you've seen topics in Calculus 3 before. If I have a random vector v equals 1, negative 2, we can compute a unit vector that is in the same direction of v using these ideas of lengths. So let's compute that by first sketching out what this looks like. Here's my vector v at 1, down 2. Through this line going through the origin is the span of v. And when it says we want a unit vector, it just has to have length 1. In the same direction of v means it has to be on this end, somewhere, wherever the length is going to be 1. If we were saying the opposite direction, we would be on this end, across the origin, on this spot. So the vector u that we're going for is going to be somewhere on a unit circle, somewhere along that circle of radius 1, maybe about there if I try to visualize it. So u should be somewhere there. And the trick to this is we just need to rescale v. We took 2 times v, it would land up right over here. If we took a half v, it would land somewhere over here. So we need to multiply by the right scalar that just makes the length of v itself exactly 1. The trick to this is you just say u is going to be equal to 1 over the length of v, rescaling v. So whatever the length is, if you multiply by 1 over the length, you've normalized the length of that vector v to exactly a 1. So we can break up the computation and just say compute the norm of the vector v itself. That's the dot product v dot v, square rooted, which means this is the square root of 1 plus 4 once we multiply those two together. So v dot v gets us this result. Square root of 5 is the outcome. So the length from the origin to here is square root 5. You can force it to be a length 1 by just dividing by the square root of 5. So that unit vector u we'd like is u equals 1 over the square root of 5 times the vector v. That just means we're rescaling both of these components. Now it's 1 over root 5 and negative 2 over root 5. So that's the exact entries you would have to have with some spot on the unit circle to force u to have length 1. It's in the same direction because it's on this end, not across on this opposite side? Well, that's one thing the norm gives us, a notion of unit vectors. Really, the next exciting thing about norms is distances between vectors, which leads into angles between vectors. But this is a good start so far. Any questions at the moment, folks, with the tour of the dot product tools? Okay. Well, next concept is calculate the length of negative 82 times v. If it was negative v, we would just be over here. And we already know that length. It's 1 over the root, excuse me, it's square root 5 itself. If it was negative 2 times v, we would be over here. And that would just be twice the length of v in the opposite direction, sure. But that means this computation really doesn't have to be as hard as it looks. You could just rescale this by negative 82, square the components. So you'll have 82 squared, 164 squared, or 164 after squaring rather. And then you have a complicated square root to simplify if you decided to simplify it. Or this theorem is kind of just telling us what we would expect. The length of a rescaled vector is whatever that scalar is, positive or negative. Take the absolute value of it, multiply it by the length of that vector. So if we want to do the length of negative 82 times v as fast as possible, it's really not a big computation. We'll take advantage of this idea whenever it pops up and make a big deal out of it. The length of negative 82 times v is the absolute value of negative 82 times the length of v, which would then be, we already have the length of v, it's root 5, it's just 82 times 5. Excuse me, root of 5. So that's a nice, clean way to do that. It's not the world's most impressive theorem, but it saves you some time whenever it comes into play. Well, that's our wrap up with the length of vectors. Next thing we want to discuss is, if you can think of the length of a vector, you know the distance between vectors. In fact, the length of the vector v is just the distance between v and the 0 vector, so it already is giving a distance. So here's the formal definition. Our author likes to use this symbolism here, using dist, short for distance, as kind of function notation. So this is a bona fide function, takes two vectors from the same vector space, and the definition of what we mean by distance is the length of the vector difference, u minus v. So that's it. If we can define the norm of a vector, we can also find the distance between them. So that's what we'll practice on example 3. But we see it also leads into the bigger concept that we want to get into. This section says inner product and orthogonality. Orthogonal means your vectors are perpendicular. The angle between them are 90 degrees, or pi over 2. So to get to that concept, we need to know, how do you get the angle between vectors in the very first place? Really, this is the only missing tool at the moment. So we'll see how this goes, and then mention a bigger shortcut theorem that could be used in a more generic case. First thing we want is the distance between those two vectors. So let's calculate u minus v to start. This will be 3 minus 7 for a negative 4, then 4 minus 1 for a positive 3. So distance between the two is distance uv, which is just the length of u minus v, which is the dot product of u minus v, dot product with itself, square rooted. But that means you just take the entries, square them, and sum them. So this will be 16 plus 9 for a nice square root 25, giving us a length of exactly 5. So we got it. That's the length of the vectors, 5. And somehow, some way, we can use that to get the angle between the two vectors. It's not really clear how you would do that unless there's a picture to look at. So to organize our thoughts, let's draw out the picture for this situation. So first vector is that 3, 4. This gives us the vector u, and here's the subspace of R2 that contains that vector. Here's span u. Now, next vector is 7, 1. So here's 3, 4, 5, 6, 7. Height 1 gives us the vector v. This one's kind of challenging to plot. Let me just make that a bigger dot. So here's vector v, and this is span v. And then finally, we calculate the distance between those two vectors. So that's this line segment going this way. And we found that that distance, norm, u minus v, is 5. So we have the length of this vector. But you know what? We have the length of this vector too. If we just calculate norm u, we have the length of this vector as well if we calculate norm v. And what we want is this angle theta. When it says find the angle between u and v, that's what this next part B is really asking us to find. So here's a picture so far with distance and the angle thrown in. Next, we'll find that angle and see what the measurement would be between those two vectors. Any questions with the diagram or computation so far? Okay, it's kind of a nasty triangle because there's no right angle inside of here that visually looks like there'd be a right triangle or right angle, but we can still use a nice tool like the law of cosines to get that angle theta. So law of cosines would say, just to make it a little bit less abstract, let's break that triangle out of the xy plane or x1, x2 plane. We have length 5 going this way. On this, we have, let me put in the theta first so I don't forget about it. On this segment, we have the length of u. So let's compute norm u. U is 3, 4. So take 3 squared. 9 plus 4 squared, 16. That's kind of a nice coincidence. We have square root 25, giving us a 5. So it's like the numbers are kind of just rigged to be nice on this problem. On this segment, norm v is another computation we need to pull in. So go back to this. The norm of v is going to be square root 7 squared plus 1 squared. So we got a root 50 out of this. And just in case it's handy, let's simplify this down to a 5 root 2. So 5 root 2 or root 50 on this end. Now the law of cosines is going to be able to give us that side length 5. So we can say, let's mention the tool because this is another just random trigonometry fact leaking into the notes. Law of cosines is essentially just giving us an extension to Pythagorean's theorem. If you imagine that's the hypotenuse, which it isn't, but if it was, you would say the hypotenuse would be 5 squared equals the lengths of the other leg squared. So that'd be 5 squared here, plus 5 root 2, or more simplified form for this purpose is root 50 squared. Easier to square out visually. So that's what Pythagorean's theorem would say if we had a 90-degree angle, and that was the hypotenuse. But that's false, so law of cosines gives us the corrective factor, term rather, minus 2 times 5 times root 50. So those legs just come back into those two same spots. Just multiply this time with a minus 2. And then here's cosine of the angle theta, the thing we want to solve for. And that's not too bad to deal with, just a lot of arithmetic to run through here, and we can solve for theta. That'll give us the angle between the two vectors, and this kind of little trick can always be done. In fact, it could be done a little bit more fast when you start to really look into what was going on here. It turns out when you work with norm u minus v squared, you can start simplifying these things. Same with norm v squared into a slightly more compact formula. We're doing it this way from scratch just to visualize what that formula, where it even came from in the first place. So working through this, we'll have a 25 equals 25 plus 50. And here this is going to be, you know what? That was probably more convenient as a 5 root 2 on the spot. Let's put in a 5 root 2, the simplified version. Root 50 is a 5 root 2, and that would give us now negative 50 root 2 on that one. Cosine theta. So we've got, say, 25's cancel, subtract 50 from both sides, negative 50 equals negative 50 root 2 cosine theta. We can divide both sides by negative 50 root 2 to get positive 1 over root 2 equals cosine theta. Now we need to find that angle theta, but this is one of those weird times where rationalizing the denominator is probably a good idea because you might have more muscle memory or from rote memorization if you saw this as a root 2 over 2 equals cosine theta for coming up with that angle theta now. Well, root 2 over 2, that's going to happen when either sine or cosine at pi over 4 is the angle theta. So pi over 4 or 45 degrees will give you cosine and sine at root 2 over 2. So right at this step, we can say the angle between u and v is theta equals pi over 4. And it kind of looks like pi over 4. That looks like it'd be about 45 degrees. It's not perfect, but that's in the right neighborhood of that kind of rotation. So now, after defining length, then length between vectors, we can now get angles between vectors. And that's what this section is all about when it's titled Inner Product and Orthogonality. The more particular angles we're mostly interested in is pi over 2. Pi over 2 is an important angle because if the angle between those vectors was pi over 2, 90 degrees, they would have been what we call perpendicular vectors, or more often called orthogonal vectors. Properties of orthogonal vectors are very massive, and that's what chapter 6 is all about, coming up with orthogonal bases and the different things you can do with them. In fact, statistics, regression analysis, is just based on this whole idea that we're getting into. Well, any last questions, folks, on getting that angle? Okay, down below I had the quick blurb that we looked at last class saying if you take a space like a functional space, polynomials or continuous functions like C01, you can give these our inner product as well. Once you have an inner product, you can equip it with a norm, just like we came up with a norm, like the norm of u minus v. And you can redo all of this in a very, very abstract vector space. You can ask and answer questions about what are the angle between two random functions. This kind of stuff is getting into other concepts like in engineering mathematics, like Fourier series and that kind of analysis. So all these ideas just keep on extending further and further. And this space just keeps on coming back over and over again, which is interesting. But let's get back onto the main topics. We're defining angles and now specializing into really important ones. First, if you want to solve this problem to get any angle between two vectors, this is the formula that I was mentioning. It actually simplifies way down to this. When you do a lot of the algebra on the inner products and the dot products, you get this as a result, which is pretty surprising. It simplifies down to just that much. Theta is going to be the angle between the two vectors. But notice what that means now. If u dot v comes out as 0, then, well, in that case, cosine had to involve an angle of pi over 2. Or either the vector u or the vector v was the 0 vector. That's a second case, which can come up. That will give you a dot product of 0. So in either one of those cases, if one or both of these vectors are 0, we'll call them an orthogonal vector. If it's just one or both, that would do the job. If neither one of them are a 0 vector, and the dot product still comes out as 0, that means the angle between them was pi over 2, or 90 degrees, and so we call them orthogonal in that case as well. So there's lots being said here. 0 vector is orthogonal to every other vector in Rn is an important concept as well, just as a side effect of using this equation here. The next concept is if the vectors are parallel, well, that would mean the angle between the vectors are either 0 if they're going in the same direction, or pi, 180 degrees, if they're going in opposed directions. But vectors are parallel if and only if the set UV is a linearly dependent set. So that's a kind of cool tie-in. So in this case, for parallel vectors, the angle theta is 0 or pi. For orthogonal, we mean that the angle theta between them is specifically pi over 2 or 90 degrees. So just to tie those concepts together, here's a couple pretty fast problems. First, we have a random vector u, a random vector v. The questions on both these two examples are the vectors orthogonal, parallel, or neither? And we could plot them and get a good feel for if they look like they're perpendicular vectors, orthogonal. But, our eyes can be deceiving. I can't plot on a perfect grid. So this is a fantastic tool. Just take u dot v. Multiplying corresponding entries, we'll get a -4 plus 4, which is 0. And our work is just totally done right at that step. So that's a fantastic concept already. The dot product is telling us when we get 0, specifically that these are orthogonal vectors. So let's say here, vectors are orthogonal. And it also asks for the angle between the vectors. We can say, and so, theta equals pi over 2. So pretty fast problem, not really much to say on that one beyond it. Any questions with our first orthogonality check? Okay, notice these vectors also form a basis. They're linearly independent as well at the same time, and so are the standard normal vectors, e1, e2. They're orthogonal as well, and they form a basis. Orthogonal bases, again, have lots of really special tools that go along with them, and so that's what the next few sections are going to be really all about. For another run through, here's some very different looking vectors. Same check, we're looking for orthogonal, parallel, or neither. We take u dot v, then we get on this one, -2/3, -8/3. This is not 0, so this implies uv are not orthogonal. So now it can either be parallel or neither. If they are linearly independent, that would be the neither case. If they're linearly dependent, that would be the parallel case for this one. So we have a pretty fast test for that. Let's use a determinant, invertible matrix theorem. Let's take the determinant. We're testing for linear dependence. So determinant of this matrix formed from the vectors u and v. So this would be the determinant, -1/3, 2/3, 2, -4. Multiplying the main diagonal gives us a +4/3. Subtracting the off diagonal gives us -4/3. This comes out at 0, and so we can now say that this implies immediately uv is linearly dependent from the concept above. That tells us about the vectors. They're not orthogonal, so they could be parallel, but it could have also been neither if the determinant was non-zero. But this now tells us they're parallel. Parallel vectors. So this means the angle theta between them, well, it's either 0, that's if they're going in the same direction, or pi if they're going in opposite directions. Looks like opposite directions, but let's justify the 0 pi even more by just plotting these. Let's see what this looks like as just a rough plot on this one. Let me start with the easier one to plot, 2, -4. So here's my vector v. This is the span of V, this line segment, or this line. It's not a segment, it's an entire line. So V ends up here, and I know exactly where U is. Well, not exactly, but I can plot it in a pretty decently easy way without thinking too hard, because I know absolutely it's inside the span of V. It has to be. If we have linear dependence, like we just proved through the determinant, that means U is a multiple of V. And, well, because of the negative right here, it's got to be somewhere on this end. U ends up somewhere at negative 1/3, 2/3. So I'll just make a quick rough dot there. There's our vector U. Now they're on opposite ends from the origin, the zero vector. That tells us the angle between these two vectors is pi, or 180 degrees. So angle between them is pi on this problem. Well, if we got linearly independent, we would have just said neither. And that's what the last problem was all about. These two vectors right here, they're definitely not orthogonal. They're definitely not parallel. Span U, span V are distinct. This would have been a neither situation. And we definitely know it is because the angle was pi over 4, or 45 degrees. So that's our quick work on angles between vectors. Really, this is the whole pretty much big tour of the homework set. There's still one more important concept that we want to take a look into in these notes before we move on to the next. Any last questions at all, folks, getting through these examples here? Okay, definitely it's geometry, the main focus on these notes. We're drawing a lot of sketches. We'll draw even more sketches in the next section. But here are some problems that are not as easy to sketch, yet the so-called orthogonal complement is something that's going to make a big comeback in the next couple sections. This is a pretty interesting definition. It says, let W be any subspace of Rn. So once we have a subspace established, the dimension could be exactly n, but usually it's between, say, 1 and n minus 1 is the interesting cases. And if we found a vector z so that z dot lowercase w comes out as 0, that means z is orthogonal to w. The angle is pi over 2. And if this happens for every single vector in the vector space w, we say 0 is orthogonal to w. So now we can have a concept of not just vectors being orthogonal to each other, but one particular vector being orthogonal to an entire subspace of some vector space Rn. It just has to be orthogonal to every single vector inside that subspace. But once you have that concept, a vector being orthogonal to a subspace, you can build this thing. The orthogonal complement of W is denoted by W orthogonal, or sometimes people abbreviate this as saying W perp for short, because that's the perpendicularity symbol. So orthogonal complement is this set. It's a set of all vectors z in the same vector space such that z dot w is 0 for all w in lowercase w in uppercase w. This is just saying the orthogonal complement is the collection of every vector z that is orthogonal to w in the first place. So if you find one vector that's orthogonal to w, but build out all of them into a set, we have the orthogonal complement. So this one turns out to be a subspace of Rn. It's a pretty interesting subspace, and this is part of the work that we're going to be doing in the next sections, looking into orthogonal complement. So here's a couple examples on just working with this concept before we just move on to the next. What's kind of unfortunate about our textbook is it really didn't give any exercises at all on working with orthogonal complement, even though it's part of the reading in this section. They gave an example in this section. There's no actual homework exercises for this. It's kind of weird. So think of the exercises we're about to do as probably not real exam questions, but you know some of them are going to be pretty decent review questions because a null space will come up. Examples 6 and 7 really are just thinking a little bit more about this, so we have a good picture in our mind of what the orthogonal complement is when we use it as a concept and a tool in the next sections. So in this problem, we're in R3. W is the span 108, a half negative 3, 4. That means it's automatically a subspace by theorem 1 of chapter 4 of R3. Let's label these vectors as V1, V2, just for a quick reference. We want to answer the question, is the zero vector orthogonal to W? That's an important question because that would be the first thing you would want to check if you're trying to prove W is indeed a subspace. The zero vector has to be inside there. But it's not too hard of a check. You can just say right out of the gate, let's call this, how about X be in W? Well, because W is a two-dimensional subspace of R3, that just means X has to have 3 entries. It'd be X1, X2, X3. We're trying to check if the zero vector is orthogonal to W. Being orthogonal to W just means Z for the zero vector dot my vector lowercase x has to come out as 0. That's definitely the case. If you take the zero vector and take zero dot x, because all these entries are 0, we'd be multiplying all these entries and getting 0 dot x1 plus 0, I shouldn't say dot, 0 times x2, that's normal multiplication over here on the right, plus 0 times x3. And you get that 0 vector dot x is absolutely the zero scalar just by the nature of the zero vector. It satisfies this condition. Zero vector times r vector x came out as 0. This is any vector in W. Any vector in W has 3 components. I didn't choose them specifically. So we have a big conclusion. This tells us, therefore, the zero vector is in the orthogonal complement. It belongs to this set. So that makes it plausible. It is a subspace. I'll leave the full proof to the reading since we don't want to get too bogged down on staying in this abstract concept here. But the next thing we should check is, it's kind of a cop-out to only check with the zero vector to see if it's inside the orthogonal complement. A more interesting check is to see if that vector z, 8, 0, -1, is also in the orthogonal complement. What would that work look like? We'd have to take z dot lowercase w, make that come out as 0 for every single vector in W, but we know the span contains infinitely many vectors. So that seems on face value like a ton of work, infinitely much steps to do this. But it's really not so bad. We can start off like we did before. I'll change from X to a different vector. Let's call it lowercase w, like in the definition, and say this. Let lowercase w be in the vector space W itself. Because W is given as a span of V1, V2, without the span, this is a basis, we can describe every vector inside the vector space W in terms of a linear combination of these two. That's what the span gives us. That's what the basis gives us. Basis is going to give us a unique way to do this. We can say then, W is going to be equal to C1V1 plus C2V2 for some scalar, or some scalars, C1, C2, in R. Really, this is just kind of a review problem about spanning in the very first place. So here's an arbitrary vector, different from how we did it up here with X. X, we didn't have to work too hard. But if we want to use Z, something that's not just a zero vector, and dot product it with an arbitrary vector inside W, it's got to look like this, that vector W down below. So let's work this out. We can say next, then we're trying to see if we can get in this set. So we need to take Z dot W and try to get 0. So here's Z dot W. First, we can substitute. We have a nice way to write out W as a linear combination of the basis vectors. So this is Z dot product with C1v1 plus C2v2. And here's where all the properties of the inner product start to become really super helpful. Let's cite them as we use them, just as a quick reference on how we're using these properties. We only just sort of stared at them for a little bit. We haven't really used a lot of this directly. So here's how it'll go. First thing that we can do is use distributivity, property B. B is showing distribution from the right, but property A also says you could swap these out if you wanted to, put W on the other end and distribute in the same kind of way. So really both properties A and B allow me to distribute Z into that group. So this then turns into Z dot product C1V1 plus Z dot product C2V2. The scalars C1, C2 are kind of in the way, but that's what property C is all about. Wherever the scalars are, you can just move them out front and do the dot product first, rather than scaling first. So using that property, particularly where the red dot is, this turns into C1 Z dot V1 plus C2 Z dot V2. Now we're done with the properties. We can take the dot products as normal. That's kind of handy. We use properties A, B, and C. Property D was mostly to give us a sensibility on how to define length in the first place. Any questions at all, folks, with that bit of algebra there? Okay, keep in mind, if we were in a complex vector space, Cn, that doesn't work out so nicely. There's all sorts of changes. Part A is different, part C is different. Let me see here. Turns out part B is true, and so is part D, but parts A and C go haywire in complex vector spaces, which is interesting. So now back to our major topic here. We can take these dot products. Here's Z over here, here's V1, V2. So this turns into C1 times. I'm going to focus on this vector and this vector, do the dot product. So that's 8 plus 0 minus 8. Then we move on over. We need to take this new dot product. Z dot V2 means multiply those entries highlighted, multiply the corresponding entries and add, we'll get 4 plus 0 minus 4. But notice both of these come out as 0, so this is kind of the shortcut. We get 0 plus 0 times C1 plus C2 times 0, resulting in 0, and then that gives us a conclusion. We just had to have Z times W equals 0 for every vector in W, and this is every vector in W can be described in this kind of way for some choice of C1, C2. So this tells us finally, because we got 0 on the dot product, Z is in the orthogonal complement, W perp. So it's kind of an interesting and wild problem, but notice what the shortcut is. It turns out for this vector to be in the orthogonal complement of W, you just have to have that any vector in question, dot product with the two vectors spanning, or however many vectors are spanning, just has to come out as 0. If that's the case, then that's the quick check on this problem. Also notice dimension of W is 2, and that means for our W complement, we're expecting the dimension of this one to be 1. But we would have to find all vectors Z that's inside the orthogonal complement to really know what the dimension is. So that's what we're going to do on our next topic before we change gears into section 6.2. How do you even find the orthogonal complement? We showed how to test if a vector is inside it or not, but the big question is, how do we get it in the first place? Well, any last questions at all, folks, with this new definition, brand new subspace? Okay, here's where section 6.1 comes to an end. It's kind of a wrap up of the concepts we were talking about. First is really a definition. X is in the orthogonal complement if and only if X is orthogonal to every vector in a set that spans W, which is essentially what we checked with our last example. There's another comment we made. The orthogonal complement is a subspace of Rn. And this is something we said suggestively. The dimensions of the original vector space W and the orthogonal complement should result in the full dimension of the underlying vector space, which they're both a subspace to. So that's why we call them complements. They fill out a hole in terms of coming up with an entire dimension. Then finally, theorem 3 is the big tool that allows us to actually find an orthogonal complement in the very first place. Our author didn't give it the full name, but the author did state the theorem. I think it was kind of curious that most textbooks would name this theorem. If you have a fundamental theorem, people are usually kind of excited about it. Maybe it's because the author didn't use it too much. There's no exercises actually coming up with this thing. But I think it's still a good exercise for us to do for a little bit more practice with null spaces and to actually see what we're looking into when we talk about the orthogonal complement. The fundamental theorem of subspaces says, grab any matrix, doesn't have to be square, size m by n. Then the punchline is, if you take the row space of A, that's the span of the rows of A, the orthogonal complement of the row space of A is just a null space. So every null space you ever came up with is an orthogonal complement. Orthogonality is happening in the background there. That's kind of interesting in a certain sense. Here's the one we're actually going to use. If you take the column space, the span of the columns of A, the orthogonal complement of the span of the columns of A is the null space of A transpose. And that's kind of curious in a certain sense. This is a really big, monumental reflection on linear algebra that these particular subspaces, through the orthogonal complement, are related in this kind of way. And this is the big theorem for subspaces. So we're going to practice it using this part right here to come up with our own orthogonal complement, W per. So we have a subspace W. It's the span of these two vectors out of R4. We can use a different idea just to organize our thoughts on this, the theorem above. Span contains two vectors. These vectors are not multiples of each other. We can check it on entries 1. 0 and 1 tells us these are linearly independent. So the basis for W is just those two vectors, W1, W2. That means dimension of W is 2, the number of vectors in a basis. But these live inside R4, so this also tells us, by property 3 of this theorem, that the dimension of the orthogonal complement of W is also 2 as well. It's a null space, so we can write this as a spanning set, and there had better be 2 vectors, or else the dimension didn't come out right. So that's the start of the problem. We're using this part right here, so we need a matrix to use this fundamental theorem. We need to design our matrix. But if there's 2 vectors just looking at us, we can say, let A be the matrix formed by the vectors W1, W2. So the subspace W is the span of those 2 different vectors. That means W can be renamed as, if you span the columns of A, this matrix, that's the column space. So we can give W a new description. W is just the column space of A. So now this implies, if you want to compute the orthogonal complement, W per, then this thing is just going to be equal to column space of A as an orthogonal complement. All I've done here is substitute in the subspace W for a column space, but it connects back up here. The orthogonal complement of any column space is automatically the null space of that same matrix A transposed. So if we can find the null space of the transpose of A, here's the A, we're done. That's the orthogonal complement. So now it's essentially an exam review problem at this point. To find the null space of A transpose, we need to solve A transpose times X set to the zero vector. The null space is just the collection of all solutions to this system of equations here. So as an augmented matrix, we can just jump right into it. A transpose is transposing these columns. Columns turn into rows. So this is row 1, 1, 2, 0, 3. We're also augmenting it, so it's added 0 there. And this becomes row 2, 0, 1, 4, 1. Row reduction goes really fast on this one. So we have 0, 1, 4, 1, 0. We'll multiply row 2 by -2, add it to row 1, and we get 1, 0, -8, 1, and 0. So this is now in reduced row echelon form. We can take variables x1, x2, x3, x4, and fully solve this system, writing it in parametric vector form. So first thought, taking this and writing it back as a system of equations, we have x1 equals 8x3 minus 1 times x4. x2 is now equal to -4x3 minus 1 times x4. The remaining variables are free. So x3 is 1 times x3. x4 is 1 times x4. And so the solution set for all possible x's are x equals, take x3, coefficients are 8, -4, 1 and 0, plus x4, coefficients go -1, -1, 0, 1, such that x3, x4 are scalars in R. So we did it, folks. This is really a span of a different kind of set. We didn't write it with the word span, but we have parameter values. They are free variables to take any value in R. So really, the solution set to this is the null space, which is just the span of those two particular vectors. But we wind it all the way back. That null space was special. It's kind of impressive how this one weird technique, parametric vector form, is tied in with so much lately. This was essentially a major technique of chapter 3, getting eigenvectors, because null spaces come up for that as well. But so does orthogonality. Null spaces is a natural concept for orthogonal complements as well. We wind it back to this and say, therefore, the orthogonal complement to this subspace W, which is the span of those two vectors, is just span 8, -4, 1, 0, -1, -1, 0, 1. And if this is really true, if this is the orthogonal complement, then this vector dot product with this vector has to be 0, as well as with this vector. And likewise, this vector dot product with both of these have to come up as 0 as well. And you can double check that just by a really fast visual inspection. Let's focus on just this one and do the dot product mentally. If we take this dot product with this one, we'll get -1 minus 2 plus 0. So we're at a -3 plus 3 balances to 0. So it does work out. Do the dot product with this one, and we'll get 0 minus 1. So we're at a -1 plus 0, still at -1 plus 1. It balances to 0. So the dot product with this vector, and both of them come out as 0. That tells us this really is an orthogonal complement, and same for this one. But it turns out to span those two specific vectors, and you build out the entire orthogonal complement. So every single vector in this spanning set is orthogonal to every single vector in this spanning set as well. Last concept was about dimensions, but I forgot there's a part B. We kind of spilled the beans already up here. But any last questions at all, folks? Actually finding that orthogonal complement? Okay, just to finish up the notes, let's put the answer down here as well. The dimension of W was 2 because we observed we had a basis. It already spans, it's linearly independent, and contains 2 vectors. We also know that the dimension was 2 for the orthogonal complement by this theorem, but we can just visually see it. These are linearly independent vectors as well. There's 2 vectors. So these vectors taken together without the span is a basis. And it tells us the dimension of the orthogonal complement is 2 as well. These are subspaces of R4, so these dimensions have to sum back to 4 specifically each and every single time. Well, that's it, folks. That's the rundown of inner product and orthogonality. I think this problem is kind of fun because it's really just a giant review problem. It loops back with a crazy technical theorem, but the big takeaway for this is it was more about just actually finding orthogonal complement ourselves and practicing with a null space and a transpose. With the next section, we're going to put these to good work. Next section is not too long, and the final section of the course 6.3 is actually very, very short out of nowhere. So we'll probably finish the last remaining topics when we come back on Tuesday. But first, let's take a look into the next section, what we're getting into. Any last questions or comments or whatsoever before we change gears? Okay, well, this naturally leads into the next concept, sets of orthogonal vectors or orthogonal sets. And this is a pretty cool section where the work gets even more geometric than we've seen even in the last section out of nowhere. First is a really nice, interesting kind of a refresher problem about vectors being orthogonal, and just a slightly more built-up definition. We'll say a set of vectors is an orthogonal set itself if the pairwise dot products ui dot uj come out as 0 as long as I is not equal to j. That part's really important because if your vector is not the 0 vector, say none of these are 0 vectors, this vector dot product with itself is not 0 at all because it's not the 0 vector. Positivity says the only way you get ui times dot product ui as 0 is if that vector was a 0 vector itself. So every pairwise dot product of one vector with some other vector inside the set, if they always come out as 0, we say that the set is orthogonal itself. So really, it's a pretty fast check, especially if there's only 2 vectors. If we label this, say, u1, u2, then we'll take u1 dot u2. That's negative 12 plus 12, which is 0. And then our work is done. u1, u2 is an orthogonal set. And it's also an orthogonal basis at the same time. So let's make that a quick comment. Also, an orthogonal basis. How do we know it's a basis? Well, they're linearly independent. They are not multiples of each other because if you multiply that entry by 3 to get negative 6, it doesn't work on the top entry. Multiply this by 3, you don't get a negative 4, you would get a 9. So they're 2 vectors, they're not multiples of each other, meaning they're linearly independent. But a set of 2 linearly independent vectors is automatically a basis. So we get a basis out of this one. So that's what we're doing just in this first warm-up exercise, determining if the vectors are orthogonal. And give reasons for your answers is really just doing a bunch of dot products. This one's different because it contains a 0 vector. So if we label this as, say, v1, v2, v3, this one goes pretty fast as well. v1 dot product v2, we're multiplying the 2 corresponding entries from the 2 vectors here. We'll get 0 minus 2 plus 2 comes out as 0. v1 dot v3. So on the opposite ends, well, that's the 0 vector. It's just automatically going to be 0 as a scalar. And then v2 dot v3. Well, because v3 is a 0 vector, we just get 0 as well. They all come out as 0 when we form all the pairwise different dot products. Thankfully, with commutativity, we don't have to worry about, say, v2.v1. It's the same as v1.v2. So here we can say v1, v2, v3 is an orthogonal set. But you know what? It's definitely not an orthogonal basis. So we have to keep that thought kind of separate in our minds. Sets can be orthogonal like this one and like this one, but sometimes they're a basis, other times they're not. In fact, the only reason we have an orthogonal set of three vectors in R3 and it's not a basis is specifically because one of them is a zero vector. The set's linearly independent. So let's write this as a warning, but it is not a basis. Well, let's go on to the next one. You know, this one you can kind of do it in a little bit of faster way just by visual inspection. It turns out the next theorem we're going to look into says, if you have an orthogonal set and the zero vector is not inside that set, it's automatically a basis. So if we're looking into three different vectors here, there's no way it could be an orthogonal set any longer because there is no basis for R2 that contains two vectors specifically. I cannot have an orthogonal set of three vectors in R2, in other words. It's impossible now, unless one of them is a zero vector. That's one way to cop out of that. So if it's non-zero vectors like we're seeing, it's impossible for this to be an orthogonal set. That took a lot of words. It's probably easier to explain this just by doing the dot product. Let's see what goes wrong here. Take u1.u2. That's 4 minus 4 coming out as a 0. So it doesn't cause any problems just yet. My subscripts might. Let me change that to a u3. u1 dot product u3 is going to give us 22 minus 16, which is non-zero. And right here we can stop. We had to have all vectors orthogonal with each other for it to be an orthogonal set. The moment one dot product returns non-zero, we can immediately conclude u1, u2, u3 is not an orthogonal set. So orthogonal sets and bases tend to actually go naturally together as long as you eliminate this weird case where one of the vectors happens to be a zero vector. We have an orthogonal set of non-zero vectors. If this one was non-zero and they were all orthogonal, that would also be a basis. We wouldn't have to check a determinant. We wouldn't have to do row reduction. We would know just because we did three dot products. And that's a brand new way of determining if we have a basis or not. Something that's outside of the invertible matrix theorem, which is, again, kind of exciting when that happens. So that's the next concept we're taking a look into. Theorem 4 says if you have an orthogonal set, critically of non-zero vectors, because one zero vector makes it dependent and not a basis, but if you have an orthogonal set of non-zero vectors in Rn, then it's automatically linearly independent, and it will be a basis for the span of those vectors. If P equals n, it'll be a basis for Rn itself. So that makes these problems really, really fast. To verify if this is a basis, all we need to do is see, is it an orthogonal set? We already know there's no zero vector in sight. So let's do another set of dot products. There's a lot of dot products in this section. We want to test if all vectors are orthogonal to each other. So take v1.v2. There's really just three dot products to do. We get -4 plus 0 plus 4 comes out of 0 in that one. Take v1.v3. So the outside vectors will get -16 plus 17 minus 1. Miraculously, that's -17 plus 17 for 0. v2.v3 comes out as, so the last two vectors, 4 plus 0 minus 4 comes out as 0. And you know, this is pretty exciting. These three zero values here tells us that v1, v2, v3 is an orthogonal set of non-zero vectors, it's linearly independent then. Three linearly independent vectors inside R3 automatically forms a basis. So we're done. This tells us, therefore, it is a basis for R3. And it's a good time to kind of appreciate why this is such a powerful technique. Orthogonality is kind of special in a certain sense, because if we had to do this from scratch, you're possibly doing a determinant of a 3x3. Not the worst thing in the world. The row reduction might have been worse. But I think everyone agree this is the path of least resistance. The moment you detect those vectors are orthogonal, it's automatically a basis. There's no further computation whatsoever, making this a particularly powerful theorem at our disposal. Next, we're going to put this theorem to good use. If we know we have an orthogonal basis, we can do other things really fast, like linear combinations we're going to see in the next problem. Any questions at all, folks, with the rundown on this example here? Okay, here's how the next concept goes. This is the linear combinations theorem. In fact, this little computation here comes back over and over again. It's tangled up with something called the projections of a vector onto a subspace. So here's a thought, or here's the rundown of this theorem. You start off with an orthogonal basis. If you don't have an orthogonal basis, then you better check if it's orthogonal. If it isn't, this theorem is totally off the table. But if you do have an orthogonal basis, then every vector in that subspace W for which you have that basis, it can be written as a linear combination in a really rapid way. Here's a linear combination, and the scalars are just a whole bunch of dot products. The proof of this theorem is really kind of interesting in the reading to take a look into. It goes through just what we mean by a basis, using dot products to just generate this as a quick result. We'll practice it just as an application rather than proving it. I think in the last couple of days of the semester content, a derivation is probably not the funnest thing in the world. So let's show how it goes. First, we have a basis B here. We should connect the thought that we were warning about. Nothing in the problem said it's an orthogonal basis, so we really should check. Let's call these vectors u1, u2, u3. It's a fast check. Take u1 dot u2. That's going to be 6 minus 6 plus 0. So we're 1/3 of the way done. u1 dot u3. So the outer vectors will give us, as a dot product, 3 minus 3 plus 0. So far, so good. u2 dot u3. So the last two dot product gives us 2 plus 2 minus 4, which is 0. And that's good. That's what we want to show. All these vectors are orthogonal to each other. So we can say B is an orthogonal basis. That means we can use a theorem. And you don't have to use a theorem. You could put this in a matrix A, augment it with Y, and just start doing row reductions. But a lot of the row reductions we've done in the past have been really, really rigged numbers so that we didn't get hung up on a whole bunch of fractions. This is one of those random problems where the numbers aren't rigged in a nice way. The row reduction might be torture to get through on this one. Yet, we could still do the linear combination without augmenting the matrix whatsoever. We just use these as scalars. So here's the next thing. We can generate the full linear combination just through that formula right there. Here's how we can organize it. Let's just write out, say, the numerators, y dot u1. We're taking the dot product of y with u1 to get 15 plus 9 plus 0 for a 26. So that's going to be the first numerator. The next numerator is going to be y dot u2. So multiply through here, we get 10 minus 6 plus rather -1 for a value of 3 altogether. And then last, y dot u3 gives us 5 minus 3 plus 4. So we get altogether on that one a value of 6. That's all three numerators put into a spot. Now let's do the denominators for each one of these corresponding numerator. The denominators go u1 dot u1. So that's the square of the length of every one of those orthogonal vectors because there's no square root there. So u1 dot u1 is just going to be 9 plus 9 plus 0 for an 18. u2 dot u2 is 4 plus 4 plus 1 for a 9. And u3 dot product u3 is just going to be 1 plus 1 plus 16 for an 18. So now we've got all the numerators, we have all the denominators, and this random vector y, 5, negative 3, 1, can be expressed as a linear combination of those basis vectors by writing y equals, going down the line, change this to a C1 to get your first C1, just means you're doing y dot u1 divided by u1 dot u1, so it's 26/18 times u1 plus, likewise, go down a row, 3/9 times u2 plus the final row, 6/18 times u3. It says express it as a linear combination, and our work is done. We don't need to multiply these through. We multiplied, rescaled u1 by 26/18, same with these, and then did all the vector additions. That's us just checking our work to see if we really get -5, -3, 1 back. What it really wanted was a linear combination, so this is pretty much it. Really, all we would do is simplify the fractions a bit. Divide by 2 here to get 13/9 u1, then a third u2, plus a third u3. So that's a linear combination. If we did the painstaking row operations like we would have in a chapter 1 approach, neglecting the fact that we have orthogonality right here, it would have been painstaking because these numbers do not look friendly for that linear combination. But we got it, folks. This gives us just a new tool, another way to do those same kind of problems like from before. Well, any last questions at all with these initial topics in this section? Okay, we're kind of shy on time, so let me give you kind of an overview of what we're going to do on Tuesday. Really our last lecture content before we start reviewing next Thursday. What we need next is a way to decompose a vector y into an orthogonal projection and a component that's orthogonal to some other vector u. Once we see how this goes and look into the geometry there, we'll get into the big theorem that some vector y, here's that same exact process that we just did in our linear combination, can be broken down into the orthogonal projection of y onto u and the component of y that's orthogonal to u. That's the orthogonal complement that comes back again. So we're going to be able to see how all this works with the major goal of finding the distance from a random vector y to a subspace. A line through u and origin is just the span of u, so that's a subspace there. Section 6.3 is the same thing, except the subspace is higher than dimension 1. We might have dimension 2, dimension 3. We want to find the distance from that vector to a higher dimensional subspace in section 6.3. But really, it's just more terms that look exactly like that. It's kind of a mysterious amalgamation of algebra right there that gives you lots of interesting stuff. So that's what we're going to be looking into next section, sexually finding distances from vectors to subspaces. And that's what loops back to the concept of, in statistics, regression analysis. The line of best fit is really doing this kind of work. Well, we'll call it a day at this spot right here. Any last questions or comments at all, folks, before we call it a weekend? Okay, well, have a great evening, everyone. If any questions come up, as usual, while you're doing the homework, don't hesitate to reach out. I'll be happy to help. Section 6.3 is going to be the last section of the entire semester, so we'll be reviewing on Thursday, a week away from today. You can take a look into the review materials that are posted here. I'll be posting extra review materials for us to go through as a class as well when we're back a week away on Thursday. But have a great weekend, folks. Try not to work too hard. I'll see you all on week 15.